I want to continue our discussion of energy use by talking specifically about how us humans use energy. Myself and you and every other human on this planet runs on chemical energy. We have to eat food every day in order to maintain our energy, in order to keep going and stay alive. So let's spend a few minutes talking about energy use and efficiency in the human body. And let's start off by just doing a real quick example. A person lifts a 20-kilogram box from the ground to a height of 1 meter. A metabolic measurement shows that in doing this work, her body uses 784 joules of energy. What is her efficiency? We know that efficiency is useful energy out divided by total energy in. And so let's apply that to this situation. Okay, well, what goes in here? What's our useful energy out? What's the point of lifting this box? The point of lifting this box is to create gravitational potential energy. Now, what's the total energy in? Well, that's how much energy we got from our food, right? Because that's how humans run, right? We digest food, get energy, do stuff with it. So that's the total energy in is from our calories. And this is our metabolic energy. So when you see this word metabolic energy, metabolic power, that's talking about how much energy we burn, how many calories we burn. So this is how many calories you burn that goes on the bottom. And so this would be, well, let's call this our metabolic energy. Okay, so our metabolic energy goes down there. And maybe we could also add a little thing here that's calories burned. And I guess what I mean here is sort of a colloquial use of the word calories, right? This is just how much energy we are burning, right? Now, calories is just a unit, right? So whether it's joules or calories on the bottom here, what I mean is just how much food energy did we burn, right? So, looking at this then, we have efficiency equals mgh over metabolic energy. And so what's the mass? It's a 20 kilogram mass. How high did I lift it? 9.8, sorry. How high did I lift it? 1 meter. And divided by 784 joules. And when we run this, we get 0.25. Or 25%. So 25% efficient. And that's a typical value. So we're going to find, we're going to use that value over and over again. Everybody's metabolism runs slightly differently, but in this class, we employ the typical human quite a lot. And the typical human has an approximately 25% efficiency, which means that of every calorie that you eat, let's put it this way, out of every 100 calories that you eat, 25 of those calories go towards doing something useful. Lifting a ball, throwing a ball, something. The other 75 joules, they just create thermal energy, which you have to get rid of somehow, which you do by sweating. We'll talk about that in the next chapter. Unless you're told otherwise, you can assume that the efficiency of a human or any animal is 25. Let's use that 25% in another example. Okay, a 75 kilogram person climbs the 248 steps to the top of the Cape Hatteras Lighthouse, a total climb of 59 meters. How many calories does this person burn? Okay, so again, it's not obvious that this is a question about efficiency, but it is. This is a question about the efficiency of the human body. Remember that efficiency, we can think about it in a number of different ways, right? It's the useful energy out divided by how much total energy you had to consume in order to make that happen. And much like in the last example, what's the point of climbing this lighthouse? Well, to create potential energy. And so once again, we are creating gravitational potential energy And we are burning energy or using metabolic energy in order to make that happen. When I ask how many calories did I burn, this is what I'm asking for. And so we can rearrange this and we can say metabolic energy equals U grav divided by E. This is, of course, mgh. And here we're going to use our typical efficiency of the human body, which we got in the previous example of 0.25. And so now we can really just kind of plug in our numbers and then run our calculator. So mass is 75 kilograms, 9.8, and how high? 59 meters. Divided by 0.25. How many calories? Well, we just got to run our calculator. And when we do, we ran our calculator, we got 173,000 joules. Does that answer the question? Well, kind of. How many calories did you burn? Well, we've answered the question, how much metabolic energy did this person use? But what we haven't done is convert that into calories. And so let's talk a little bit about the unit, a calorie. A calorie is defined as how much energy is required to increase the temperature of 1 gram of water by 1 degree Celsius. So that's what 1 calorie is. But that's not what's on your package of food. If you look on a package of food, that is actually a kilocalorie. So a kilocalorie is 1,000 calories. I haven't said anything surprising yet, right? But those calories that are on your package of food, they're not these calories. They're actually kilocalories. And there's this convention that we use that's just a horrible convention, but it's what we're stuck with. So it turns out that people call this 1 calorie with a big C, and that equals 1,000 calories with a little c. Oh boy. So 1 big C calorie is 1,000 little c calories. These are the calories that are on your package of food, not these calories. These are scientific calories. These are food calories. Our conversion is 4,190 joules is 1 food calorie. So it's a goofy unit. It makes like 5,280 feet in a mile look like it makes sense. This is super goofy. It's hard to keep track of, but suffice to say, I'm never going to talk about these calories in this class. We'll talk about big C kilocalories in this class. So let's convert this to calories. 1 calorie, 4,190 joules. Let's get out our calculator. 41.4 calories. 41 calories. Kind of depressing. So it goes. Some of us could stand to run up the Cape Hatteras Lighthouse a few more times. Okay. Here's a clicker question. When you walk at a constant speed on level ground, what energy transformation is taking place? Well, let's see. We're talking about a person walking, and people run on chemical energy, always, right? So if you're talking about a human, then we all run on chemical energy. So it's definitely chemical to something. Constant speed on level ground. Chemical to gravitational. I'm not creating any new gravitational potential energy because I'm walking on level ground. I'm not creating any new kinetic energy because I'm walking at a constant speed. Therefore, the conversion that's happening is chemical to thermal. I'm burning food calories in order to create thermal energy. That's the point of my existence. So, this kind of tells us how this idea of efficiency as applied to the human body, it's a little bit tricky, isn't it? Because sometimes we burn calories without accomplishing any useful energy out. And that's because our body just has to maintain these processes, right? And so even just hanging out, doing nothing, we use about 100 watts. And we call this the basal metabolic rate. And so here's this guy. He is just, he's hanging out on the couch. It's hard to imagine this person expending fewer calories. I suppose he could set his beer on the floor instead, perhaps. But even just doing nothing, this person is running at about 100 watts. And as soon as we start doing something else, our metabolic rate is a bit higher. And this is kind of interesting. You don't need to memorize these numbers or anything, but where does this 100 watts go? Our liver is using some energy. Our brain, your brains are using much more than this now because you're thinking very hard. Heart, kidneys, skeletal muscle, the remainder of the body. So all our organs are all pulling some power out, right? And so even just hanging out, we're using some energy just hanging out. And the more active we become, of course, the more energy we use. Here's, again, these are just typical values. For different people, it would be different numbers, right? So typing, you might have a rate of 125 watts, and you can just kind of go through it here. Ballroom dancing, everyone's favorite exercise. What else? Cycling, walking, swimming, running, right? Increasing as you go down. Okay, so that's your metabolic power for a typical individual. Okay, let's do an example. So there's a class of problems in this chapter that are like this. How long do you have to work out in order to burn off a piece of pizza? How far do I have to ride a bicycle in order to burn off my Chipotle burrito that I had for lunch? There's a whole class of questions like that. And so let's do one here so we can kind of see how they work. How far could a 68 kilogram person cycle at 15 kilometers an hour on the energy in one slice of pizza? Okay, so how far? Well, what we need to do, we need to have two pieces of information that we need to collect in order to answer this question. Those two pieces of information are how many calories, how much energy is in a slice of pizza. And the other piece of information is what is the metabolic rate of a person cycling at 15 kilometers an hour. And so those are in those tables, which I previously gave you. They're also in your book. So we're talking about cycling at 15 kilometers an hour. So the metabolic power for this first question, for cycling, is 480 watts. And remember that a watt is a joule per second, right? The other piece of information that we need is how much energy is in a piece of pizza. Of course, every piece of pizza is different. Depends on whether or not you ordered the anchovies. We need to look at table 11.2, and that has approximate energy content for various foods. And on that table, you will find that a slice of pizza has 300 calories, or about 1,260 kilojoules. Okay, so it says how far could she run? So first what we need to do is figure out how long she has to ride her bike in order to work off all of the calories in one piece of pizza. So how far does she have to ride? Now, something that is a little bit of a tricky thing that isn't necessarily obvious is that this business with the 25% efficiency, that's already included in this metabolic power. So we don't need to further include the 25% efficiency there. So what we can do then is we can just use our equation that says that power is equal to delta E over delta T. Solving for delta T, we get delta T equals delta E over power. And so, plugging in our numbers, we get delta T equals 1,260,000 joules divided by 480 joules per second, right? And so we see here, units-wise, I wrote this as a joule per second instead of a watt, so we could see that the joules cancel, and I'll end up with a unit of seconds. And so, when I run my calculator, I got 2,625 seconds. Which I can convert to about 0.73 hours. Okay, so about 0.73 hours, or 3/4 of an hour, which is a little bit depressing too, because that's a long time on a bicycle for one piece of pizza. But it's a pretty legit number. I'm going 15 kilometers an hour, so I need to go distance equals velocity times time. 15 kilometers an hour times 0.73 hours, and I got 11 kilometers. Okay. Okay, so she can go 11 kilometers if she's cycling. What changes if we're talking about how far she can run? Well, we still have the same energy in our piece of pizza, but now we should use, for our metabolic rate, we should use 1150. Well, let's see how that changes. Nothing changes there, nothing changes there. Ooh, here's where things start to get different. And when I run my calculator here, I get 1,096 seconds, which is about 0.3 hours. And so then plugging that down here, and running my calculator, we get about 4.6 kilometers. Okay, so could definitely not go quite as far if we're running as if we're riding our bike, something you probably would have guessed. Chemical energy from food is used in each of these activities, right? Like I've said many times, humans run on chemical energy. What happens to this energy? What form does it end up in? Well, whether I'm riding the bicycle or whether I'm running, in the beginning I was stopped, in the end I was stopped. This assumes I'm running over at a constant speed and not going uphill or downhill. Right? The only energy I've created is thermal energy. So in each of these cases, I'm just converting chemical energy into thermal energy. And indeed, no matter what I do, that's pretty much what happens, right? Like that's what humans do. We convert chemical energy into thermal energy.